Hello, everyone, and welcome to the third session of the DEM and CFD-DEM with PhasicFlow. Today, we are going to talk about post-processing in PhasicFlow, and also we are going to use the new solver, granular, which is the solver for coarse graining simulation. I am Hamid Reza Nourouzi with my friend and colleague Bahram are going to present this lecture to you. Bahram, please say a hello and a few words about the last two sessions and the topics that we covered in the last two sessions.
Also, hello from my side. Very welcome back to our lecture series. So I hope that you have been following us in the last two lectures. So in case that you have not done that, they are already available on YouTube. Please feel free, go and check them. In the first lecture, basically, we went through the basics of DEM and we did the first case setup, a very simplified case setup using PhasicFlow. And then in the second lecture, we continued by doing the simulation, a DEM simulation in a more complex geometry. So the first simulation was a rotating drum, and the second simulation was a conveyor. So if you have seen them already and you have questions, please feel free to ask them. That's also true for this session. So, and we would be very happy if you communicate with us. If there are any questions, please put them in the chat. So either Hamid or myself will try to check them and try to answer them. So Hamid will do the teaching, and I will be here to support him. If there are any questions or points, please feel free. So Hamid, please.
Thanks a lot for your nice introduction. As I told you, we are going to talk about the post-processing tools in PhasicFlow. And in the second half of this session, we are going to talk about coarse graining in DEM simulation. One of the cool features in the PhasicFlow is the post-processing tools that are available to post-process DEM results. As you know, as similar to CFD, when we are doing DEM simulations, we are dealing with a huge amount of data, and these raw data sometimes are not the final results that we are hoping to get from a DEM simulation. For example, if you are doing a kind of mixing simulation, granular mixing, you may want to calculate lacy mixing index or other indices that are used for quantification of the mixing process. The direct results of the DEM simulation do not give you the mixing index, and you need to do a kind of post-processing. For example, the other example could be particle tracking in the granular system, in the fluidized bed, in the mixer, and any type of the granular mix system that you are dealing with. Is the particle tracking. And for example, in the particle tracking, you may want to calculate the residence time, the circulation time, and other parameters that are related to the particles. So without that, okay, we need a kind of tool that get the DEM results and perform a kind of a special operation on the results to somehow process the DEM results to obtain new variables and quantities. The topic that I'm going to cover is located under PhasicFlow source folder, post-process data folder. As you see here, we have provided a very lengthy README file that explains different parts of the post-process data module in PhasicFlow. I'm not going to cover all the points. If you are interested, you can refer to this README file and go through the line by line to see what is available and what you can do with this module in PhasicFlow. But I'm just going to talk about a little bit about the main parts and how you can set up a very simple post-processing file and module in PhasicFlow.
Maybe a question. Does this module get compiled by default when we are installing PhasicFlow, or do we need to install and compile it separately?
No, it gets compiled in the normal installation of the PhasicFlow. But if you want to use it during the simulation, you need to include a library that is associated with this module in PhasicFlow. I explained it during this session, how you can do that.
Okay, great. Thank you.
You're welcome. Post-processing or post-process data can be executed in two modes, in simulation and post-simulation. In simulation means that you are going to do the post-processing during the simulation as the simulation is processing and advancing. You do this, the post-processing operation at the same time from the data that is available in the RAM of your computer. This is useful when you are going to do the post-processing more frequently than the more frequently than you want to save the data of the DEM on the disk. Somehow, for example, you want to save your DEM data on the disk every 0.1 second on the disk, but you want to perform and execute the post-processing every 0.01 second. So this is something that is that can be done, and you can execute the post-processing during the simulation or in simulation. The other option is the post-simulation. From the name, it's clear that you perform the simulation first, and from the results of the simulation that is saved on your disk, you can perform the same operation and perform the post-processing operation for your DEM result. The main configuration of the file that provides the information for post-processing is as follows. As it says here, you need to provide a dictionary file here. The name is postprocess data dict, and it is located under the settings folder. The main configuration of the file is something like this. We have some switches here. For example, if it is active or not active, the shape type name should be provided here. We should provide a default time control here, and then at the end, we should provide the post-processing components that could be a list of the different components that we can define for post-processing. The first one is the runtime active. If it is yes, of course, it activates the post-processing during the simulation. If it is no, it deactivates the post-processing during the simulation. The shape type is important, especially when we are dealing with the post-simulation data processing. If, for example, we are running sphere GraphFlow, the shape type name should be sphere. If we are running grain GraphFlow for DEM simulation, the shape type should be grain. We also provided a timer here. This is a common or default timer that is defined here. If we want to, for example, use the same timer for same time control mechanism for all the components, post-processing components, we can use the default in each component. Okay, but we can override this default time control by defining a new time control in each component of the post-processing data. As the line says here, you can have the post-processing during the simulation or in simulation mode. You just need to make some changes in the settings dict file. The first change is to include the library lib postprocess data.so. This is the name of the library of the post-process data. And you should also provide the auxiliary function name. The name also is post-process data. By changing these two parts in the settings dict file under settings folder, you can activate the post-processing operation during the simulation or in simulation. As I told
Maybe a
you,
question from my side, are these settings runtime modifiable or not? So I mean that when the
no, no, no,
simulation is running, if we change something, will it take effect?
no. We don't have anything like that in PhasicFlow. You should change or you should save or do all the settings before the start of the simulation. And as the simulation starts, the code or the solver reads all the dictionary files from the disk, and any changes to the files during the simulation has no effect on the simulation status.
Okay, great. Thank you. Meanwhile, we also
Yeah.
have two questions in the chat, but they're basically targeting the coupling, the CFD-DEM coupling, and I would explain them later as soon as you are in a state that you need a few seconds to set something up. Then I can go back to these questions.
Okay, thank you. About the time controls, because we don't want to perform post-processing operation every time step. We need to define a kind of mechanism to control how frequently we want to perform this operation. We have a list of the options. For example, time step, it means that everything is controlled based on the time step. The time step starts from 0, and every iteration, the time step increases by 1. The other option is simulation time. It means that the timing is controlled by the exact or actual time of the simulation. The other option is default, which means that everything that is defined in the default time control is used for that component or for that time control option. The other option is settings dict. It means that everything that is defined in the settings dict dictionary under the settings folder is also used here as the time control option for that component. We have some processing methods. For processing methods, we have actually two types of the processing methods. The processing methods that are used to calculate a kind of bulk properties like solid volume fraction, like average velocity of the particles, like concentration of the specific particle, and so on. These are the bulk properties. We calculate the bulk properties from the individual individual particle properties. We also have another processing method that is used to calculate or obtain the individual properties of the particles, like the position of the particle, the velocity of particle, and so on. And as you see here, we have a list of the options here. The processing method could be arithmetic, could be uniform distribution, could be Gaussian distribution. The first three are used for calculating the bulk properties, and the last one is the particle probe. It means that we are probing individual particles to get their properties like velocity, position, acceleration, and so on. So these are the processing methods that we use in the post-processing, in each post-processing component. And we should define a region for the post-processing. Maybe I want to calculate the average velocity of the particles in one specific region, or in a list of the regions, for example, in the list of the spheres that are defined in the simulation. Okay, then I need to define a kind of region. We have a list of the options here. Sphere, it means that I am going to define a spherical region in which I want to calculate the bulk properties of the particles, average velocity, concentration of the particles, or volume fraction, and so on. The other option is multiple spheres. From the name, it's clear I can define more than one spherical region to do the post-processing. The other option is line. It means that I'm defining a number of the spheres along a line. A box, a cubic region is defined. Rect mesh or rectangular mesh defines a kind of mesh, a rectangular mesh for you, and calculates the bulk properties in each individual cell of this rectangular mesh. This is the one that we are going to use in this session. The last four are center points. This is used only when the processing method is particle probe. So sphere, multiple sphere, line box, rect mesh are used when we are setting the processing method to arithmetic or uniform distribution or Gaussian distribution. But the last one is the center points, which is used when and only when the processing method is particle probe. Yeah, this is the region type.
Question from my side: if you want to extract the information from not a simple sphere, but from a more complex region, how can we do it?
What is this more complex region? Can you explain it more?
So, for example, instead of having a sphere, having a shape which like an S-shaped pipe or something like that.
You can define it in the code, but from practical point of view, I think that if you are going to use a kind of S shape, you need to define a kind of mesh structure for that S shape, because when you are going to define an S shape, you need to somehow define a mesh structure that covers the whole region of the S shape. Okay.
Can we also do it with this multiple sphere approach?
At the current, no. Multi-sphere, yeah, of course, yeah, that's a good idea. I never thought of that, because with these multiple spheres, you can define a set of spheres that form this S shape that is of your interest. Then you can, for example, perform the analysis on that irregular or more complex shape that you have in your mind. Yeah, that's a good point that you brought.
Yeah, great. Thank you very much. So basically, as Hamid already mentioned, we usually have many options, but two very common ones. Since it's an open source code, feel free, go through it and add the functionality that you're looking for. So based on the foundation that already exists, the base classes and everything is already there. So you can easily add what you want and what you have in mind to it. For example, if you want to add a complex mesh like what I had in mind, you can simply take this rect mesh thing and just extend that one. So, and going from there onwards. Or the other possibility is that if you don't want to do the programming, then you have to be a bit more creative, like the solution that Hamid already suggested, putting the spheres together to somehow resemble this S-line shape that I had in mind. So these are the two very common ways of doing the things.
Yeah, thank you very much for the complimentary explanation. Yeah, these are the region types, and you also can add other region types of your interest if you have some kind of specific application in your mind. It's fairly straightforward to add this a new region type, or even a new processing method for your post-processing operation. The other important thing that is defined in each component of the post-processing is the output format. Sometimes in some specific applications, the default precision and the default output format is not enough to represent the results. For example, the default precision is 6, and sometimes the numbers require more precision. So you can override the default settings in the output file and change the precision and the format of the output number. For example, if it is scientific or not scientific. For example, like this, suppose that I am defining a post-processing component here. The processing method is arithmetic. The processing region is sphere. This is the information of the sphere. and the time control is default. It means that it is going to use the default time control that is defined some lines above. And here you see that the precision is set to 6 rather than, sorry, 5 rather than 6. And I'm setting the output format to not to be the scientific format. So you can override this output format here. For the bulk properties, we have two kind of functions. We have average function, we have summation or sum function. For the average, we use the following equation. We have a weighting function, we have a scaling parameter, and we have a field that we are going to perform the averaging over that field. The weighting function is coming from the processing method. For example, if it is a Gaussian distribution, this weighting function is coming from the Gaussian distribution. If it is a arithmetic processing method, so this weighting function comes from the arithmetic processing method. The phi, which is called the scaling field, could be everything that is available in the PhasicFlow. For example, you may want to scale the average by the mass of the particle. For example, you want to calculate the mass average velocity of the particle. Then the scaling field should be mass of the particle. Or you may want to calculate somehow the volumetric average of the velocity. Then the scaling field could be the volume of the particle. And field is the properties that I'm going to perform operation on. For example, velocity, for example, contact force, and everything, volume or volume of particle, and everything that is of your interest. So this is the mean or average. For some, we don't have the denominator here. We only have the sum. Okay, considering these options that we have here, I can think of a lot of possibilities and a lot of operation types that I can define with these two, mean and sum, over the parameters in a DEM simulation. For example, I have provided a kind of special functions using these two. For example, average mass velocity is a special or derived function that is available already in the PhasicFlow. And by average mass velocity, we are calculating something like this. We are using average method for calculating the bulk properties, and we are using m, mass of the particle, as the scaling field, and v as the field we are performing the operation. We also have another special function here, solid volume fraction, which is a kind of summation operation. We use 1 as the scaling field. We use v, volume of the particle, for the field, and we also set or ask the code to perform a division over the volume of the region in the final results. The bulk density is also calculated using the following equation, and if I set the type of the function to the bulk density, then it calculates the following equation. The available fields that you can refer to are listed here. Position refers to the position, 1 refers to field 1, mass refers to the particle mass, density, volume, diameter, inertia, and other parameters. Some common fields are also available. Velocity refers to the particle velocity, R velocity refers to the rotational velocity, acceleration, R acceleration, contact force, ID, shape index, and contact torque. These are the other options and parameters that you can set. We also have another part that I think I missed somewhere in this file. We have some special functions that we can apply to the fields. Let me find it. Yeah. We can extract a component of the vector. For example, if you want to extract the component X component of the vector, you just need to use component function, or you want to calculate the absolute value, or you want to calculate the square root, a square of the variable, or cube of the variable, square root, magnitude, magnitude square, magnitude cube, and magnitude square root. These are the options that are available, and you can use these functions to perform an extra operation over the field, and then perform the actual post-processing on that resultant field. You can also apply kind of filtering, but I think that I want to explain the include mask during the simulation and in the post-process data dict file. Okay. Bahram, is there any question?
Yes, there are a few questions in the chat, but they are mainly about the coupling. So if I have a few seconds, then I can go through them and answer them.
Okay,
so,
go ahead.
Which method is used to resolve the particle movement in a fluid domain? Is it immersed boundary method? So basically, it depends what type of CFD-DEM coupling are we talking about. If you're talking about an unresolved one, this is not the case. But if you're talking about a resolved one, yeah, of course, immersed boundary is one of the very common approaches, which is also built in and used in the PhasicFlow Plus. So to know more about it, please stay tuned. In the next 2 sessions, we are going through the PhasicFlow. Next session will be on the PhasicFlow Plus unresolved simulation, and the session after that will focus on the resolved simulation. The next question, what should be the grid resolution in the test cases you explained? I remember you talked about the temporal resolution, but not the grid resolution, if I am correct. Basically, DEM is a meshless method, so we don't have any grid, and the grid resolution is not really relevant there. But as soon as we have the coupling between CFD and DEM, then CFD is a meshed method, and in there the grid resolution is a topic and should be paid attention. But again, these are things that we hopefully go into a bit more detail in the next sessions. The last question that we have here, as a beginner, I want to know, can we simulate the ice particles movement on free water surface based on CFD-DEM? The short answer is yes. The longer answer is with the current status of the PhasicFlow. You can just simulate spherical particles, but in some future we will also add non-spherical particles, and in there you can also have cubic ice particles. But if your ice particles are spherical ones, then of course with the current state of PhasicFlow Plus, you can also do it. But as a general comment, yes, CFD-DEM is a suitable method for doing that. It's a fluid-solid interaction coupling method. Good, Hamid, do you want to add any points to these? And just as the last one, again, I repeat it, we will go through these points a bit more in detail in the next sessions. Please stay with us also next week and the week after. So Hamid, maybe you also want to add something.
No, you already explained everything, but yes, this is the last session that we are going to talk about the DEM or pure DEM simulations, and in the next 2 sessions we are going to talk about CFD-DEM, both unresolved and resolved CFD-DEM. I already performed the simulation because it takes a long time to finish almost 10 seconds of the simulation, but I just want to mention some important parts. It is a rotating drum. The drum or the simulation contains 2 sizes of the particles. Let me just check the sizes here. As you see here, we can define the shapes in the shapes file. We have 2 sizes of the particles, 3 millimeter, the name is small sphere, and 5 millimeter, the name is large sphere. So we have a mixture of the particles in the simulation, and as you know, when we have a granular flow and the particles have a different property, like a different density or size or shape, during the granular flow, we see a kind of segregation, and the degree of the segregation is a quantity that is of my interest, and I can quantify the level of the segregation using a special uh, uh, index like lazy mix index or other indices that are available in this field. So I want to perform the post-processing on the data, but before I start the post-processing, I want to show you how you can define a mixture of the particles in the simulation. If you want to have all the particles available at the beginning of your simulation, you can use particles dict utility. Before we use this utility for positioning particle in the rotating drum simulation. If you remember from the first session, we set the shape name to the sphere one or something like that. And by default, in this default value that is defined here, I set the values for all the particles that are available in the simulation. So by setting shape name to small sphere, it means that all the particles are small sphere. Now I want to select a subset of the particles and assign another property or another variable to those selected particles. Okay. Suppose that I want to randomly select a number here. The number is 10,000 particles. I want to select randomly select 10,000 particles and change those particles from small sphere to large sphere. So in the simulation, I have at the end of the processing step, I have 20,000 because the total number of the particles is 30,000 particles. 20,000 small sphere and 10,000 large sphere. I can also set, for example, the acceleration of those selected particles or velocity of those selected particles. But here, since I'm defining a kind of mixture, the shape name is of my interest, and I want to set the or change the shape name of the selected particles at the beginning of the simulation. So this is the way that we can somehow define a mixture of the particles in the simulation. So you can also have a kind of a mixture that is that contains more than 2 types of the particle, maybe 3, 4, or even more. It is fairly straightforward. For example, you can define a selector here, and then at the end, you can also add another selector, selects another subset of the particles and assign another type of the particle to that selected subset of the particles. So the procedure is the same. It depends on how you want to define the mixture. If it is a binary mixture, tertiary mixture, or other type of mixtures. Okay, this is something that is new in at least in this simulation, and another file that we are going to cover here is post-process data dictionary or post-process data dict. It is located under settings dict. Runtime active is yes. It means that I'm going to perform the processing during the simulation. If it is set to no, it means that I don't want to have post-processing active in my simulation during the simulation. As I told you, I can provide the default time control. If I do not provide the default time control, then the default time control is similar to what I defined in the settings dict. The main part is the components. These are the components or post-processing components. I have one component here. The name is track 2 particles. The other name or the other component is on rect mesh. This is the name of the component. From the name, it's clear that here I'm going to, I want to track the properties of 2 selected particles, and here I'm going to calculate some properties on a rectangular mesh that is defined in this dictionary. Let's start with the track to particles. For the processing method, I have to select the particle probe. And as I told you, with the particle probe, I always choose center points. The selector would be ID. It means that particle selection is done based on the identification number of the particle. Or could be box. It means that I want to define a region, a cubic region, and select all the particles that are inside that cubic region. Or could be a sphere. It means that selecting all the particles in that sphere or cylinder and so on. The field, it is the field that I'm going to extract the data, or is the variable that I'm going to extract from the particle. For example, here is if I am tracking particles, I want to track the position of the particle. That's why I set the field to position. And time control is settings dict. It means that everything that is set in the settings dict is also applicable here. So let's have a look in the settings dict. As you see here in the settings dict, let me just change the coloring here. The setting is that the time control, the start time is 0, the end time is 10, and save interval or execution interval is 0.1. It means that every 0.1 seconds I want to perform post-processing operation on my data. The other component of post-processing component is rect mesh. I want to apply Gaussian distribution as the weighting function. The processing region is rectangular mesh. The time control again is settings dict. And this dictionary contains the information about the mesh. Since it is a rectangular mesh, I want to define a kind of cubic region and then define the number of divisions in each direction, in the X direction, in the Y direction, and in the Z direction, to somehow create those cells for processing. When I'm doing the bulk operation, I can define multiple operation on the same region. As you see here, I'm defining average velocity, I'm defining solid volume fraction, and also defining a small sphere volume fraction. So again, on the processing method, like bulk processing method, like Gaussian, like arithmetic, like the uniform distribution, I can define multiple operation on the same region. The first one is the average velocity, so the function should be average. The field that is of my interest is velocity. I also want to calculate the square of the fluctuation of the velocity, so I set that parameter to yes to calculate it. And the phi, the scaling field here, is the mass. It means that I want to calculate the mass average velocity of the particles. The threshold is something that is really interesting for us, because sometimes the number of the particles in the region is very small. We have a few particles, and I don't want to have I don't want to have any operations on the cells that contain particles less than the threshold, less than the value that is defined by threshold. Here, the threshold is set to 4. It means that every cell in the rectangular mesh that contains 4 and less number of the particles is excluded from post-processing. The default value is 1. It means that if we have even 1 particle, then the post-processing is performed on that cell. The other operation is solid volume fraction. The function is sum. The field is volume. And here we set we want the post-processing operation to perform a kind of a division divided by volume. It means that the result is divided by the volume of the region. This is useful when I want to somehow calculate the volumetric properties like solid volume fraction or something like that. Again, the threshold is 4. we know the meaning of the threshold here. The other operation is solid. This is just the name, but the name is something that is meaningful for us. Small sphere volume fraction, the function is average, the field is 1, and the phi is volume. By setting field to 1 and phi to volume, then I will be able to calculate the concentration. But since I want to calculate the concentration of a small particle, I need to have a kind of mechanism to somehow filter the large particles out and just keep the small particles in the operation. So that's why we also defined here include mask, and the operation for the include mask is less than. It means that everything that is less than the defined value. Here we find the information about the less than operation. The field that is going to be used for deciding or for filtering particle is the diameter, since large particle and small particle are different in diameter. The diameter of a small particle was 3 millimeter, and the diameter of the large particle is 5 millimeter. If I want to filter all the, or just select all the small particles, I just need to filter them based on the diameter, and then select the less than operation, and then the value set a value that is larger than the diameter of the small particle, but smaller than the diameter of the large particle. So by using these settings, I select only small particle, and in this way, I'm calculating the volume fraction of small particles in this post-processing operation that you see. Okay, these are the operations for the rectangular
maybe a
mesh.
question from my side. When we are talking about this averaging stuff, so basically you're assigning particles to cells. How you are doing that? So how a particle is get assigned to a cell? Let's consider that you have a particle that is like 2/3 in one cell, 1/3 in the other cell. How do you handle this part, this separation?
Okay, it is done based on the center point. If the operation is arithmetic, center point of the particle. If the operation, the processing method is arithmetic or uniform distribution. But if the operation or processing method is Gaussian distribution, then Gaussian distribution goes a little bit beyond the cell itself and takes into account the particles that are around the particle. And we also have one option to control the radius of the Gaussian distribution effect. Let me just find it here. I didn't explain, and I didn't go to into these details because just find we don't have enough to go. Yeah. Yeah, cell extension. By changing the cell extension, you can change the effective radius of the Gaussian distribution. The default is 2, but you can change it to get more effect from the particles that are far from the from the cell itself. Okay. Do you hear me, Bahram?
Yes, thank you very much.
You're welcome. Okay, as I told you, we don't have enough time to perform the whole simulation during the class, so I performed the simulation, and I want to execute the processing method after the simulation. To do that, we have a kind of utility in PhasicFlow. The name of the utility is postprocess PhasicFlow. This postprocess PhasicFlow reads the content of the dictionary file that we provided to the code. and performs all the operations that we defined there. When I'm doing a post-simulation operation or post-simulation, post-processing, all the settings that are related to the time control are ignored. It only, or it reads the content of the time folders and perform the operations based on the content of the time folders. So post-process PhasicFlow minus help. These are the options for the post-process minus flow. The one important option is out folder pass. If you want to change the default folder pass, you can use this option. You can also use the time span for the post-processing. For example, if I don't define this time span in the command line, then all the operation starts from time 0 to the end of the simulation. I also have another option, -Z. It means that whether to include the 0 folder or not in the post-processing operation. So let's start the processing. Let's have a look. Reading the point structure from time folder and then executing post-process track to particles, and then it reads ID and performing processing on the rect mesh, and on the rect mesh it also requires other fields like velocity, shape index, and diameter. And this is done for all the time folders.
So Hamid, another question: when this process is performed, where does the data get saved?
Yeah, that's a good question. Um, it is saved under post-process data folder, and for each component you will have a separate folder. For example, here we have two components, track two particles on rect mesh, and you get the same folders here, track two particles on rect mesh. Track two particles contains one file, and on rect mesh contains multiple files in the VTK format, because when I'm dealing with the mesh, I want to somehow visualize them. So having them in the VTK format enables us to visualize results in the ParaView. That's why we use VTK format. It's done. Let's have a look at the results. Track to particles. Let's have a look inside. Particle ID 10 and particle ID 25,000 are selected. This the first column is time. This is the position of the first particle, and this is the position of the second particle. And we can, for example, see how particles are moving in the simulation. Space, yeah, 9, 4. X, Y, Z of the first and the second particle. Let's yeah. This is the pass line of the particle 10 in the simulation from time 0 to time 10 that you see here. So this is the result of the first component. The result of the second component is on the rectangular mesh. So I can somehow open ParaView here. For example, suppose that I want to draw the volume fraction. So as you see here, we have a rectangular mesh and we don't have a kind of, for example, cylindrical mesh or something like that, but we can somehow filter the results using filter, threshold filter here based on the solid volume fraction, and then exclude all those cells that do not contain any particle. So, and then, okay, do we have the VDK here? Yeah. And at the same time, to get the idea how this post-processing works, we can also have particles in the paraview. Sorry. Particles. And maybe velocity of the particles. And again, this one could be velocity. Spheres, scale array to diameter.
While Hamid is setting that one up, I just also wanted to add a point here. Of course, doing a simulation which is close to the real life, which has lots of details in it, is very nice, very good. But there is also another step, another point, which is as important as doing a good simulation, and that's doing a proper post-processing on the simulation. So basically what you can see here, so even if you have the best results, if you don't do a proper post-processing, you cannot get the most out of it. But sometimes even with not having the most perfect simulation, but doing a proper post-processing, you might get information out of it, which are very valuable. And putting these things together, putting these post-processing that are done through the tools, doing the post-processing through ParaView, doing proper plotting, contour plots, graphs, and such things will help you to get a good understanding of what's happening on the background. That's what we always repeat when we have our lectures, is that what we are introducing here are tools, and you are the engineers. So you always need to take or use these post-processing tools and try to back it up or back up your conclusions with the physics. So you have to make sure that what you're seeing in the post-processing, what you're seeing from your result, is somehow confirming the physics. And if you see something does not look that realistic, then you need to go back to your simulation, into your case setup, and see what has gone wrong. So that's just a side point. So of course, this post-processing might look rather easy, but I would say that's as important as the processing step.
Yes, of course. If you cannot extract the intended information from the simulation, then what's the point of doing performing simulation? You need to extract all the useful information out of the simulation results, and that's 100% correct. Thank you, Bahram, for your explanation. Here I prepared the DEM results on the right and the post-process results on the left. As you see, I just changed the scale to have the similar scale. These are the particle scale information, and this is the post-processed information based on the cell values or bulk properties. And for example, let me just go to the last scene or the last frame of the simulation. At the end of the simulation, it takes a little bit time.
One question, Hamid, the results that you are showing here on the left-hand side, they are for small particles. Am I right?
No, all of the particles.
Okay.
On the right, this is the velocity, and I just want to change it to the diameter to see the, sorry, life. Okay. The blue particles are small particle, and the red is large part, the solid volume fraction of the small particles, which is 1 at the core of this bed and the other values in the rest. And you see the post-process results on the concentration of the small particles. And using the concentration, volumetric concentration of the particles, you can calculate the lacy mixing index and other mixing indices that you have in your project. Okay, that's all. I know that I didn't cover all the settings and all the possibilities in the post-process module in PhasicFlow, but the README file is a good resource for you. Read it. If you have any questions, just leave a comment or issue in the repository, and we will give you the hints on how you can use post-process module in PhasicFlow. For the second part, I think we have just 20 minutes. Am I right?
Yes, we have less than, we have like 18 minutes.
Okay.
Yeah, but again, I repeat it once more. So this post-processing is very important, especially when you want to somehow analyze and interpret the results. That plays a very important role.
Yes. For the second topic, I'm going to talk about coarse-graining. What is the coarse-graining? It is to represent a group of particles with a grain and modifying the contact properties to get the same particle scale and hopefully bulk behavior in the simulation. So we are deleting particles and replacing particles, original particles, with larger grains. So by doing that, the number of the elements in the simulation is reduced, and hopefully we can accelerate the simulations. The motivation behind the coarse-graining are computational time or computation time. By coarse-graining, I can reduce the computation time by orders of magnitude. By doing coarse-graining, I will be able to perform large-scale simulations. Instead of doing simulations in the lab scale, I can go to the pilot scale or even industrial scales based on the computational resource that I have. Again, a very big problem of the DEM simulation is the large amount of data that should be saved on the disk. When I'm using coarse-graining, the number of the particles is reduced, so I don't have the trouble of the saving a large amount of data on the disk, especially when you are doing a set of the simulations. Then even using a large amount of disk is not enough for your work, and you always have the trouble to find some extra space to perform the next simulation in your work. And this is something visualizing and post-processing. This is something that is hidden in every DEM simulation because with the current visualizing tools like PicPlot or ParaView, we always face problem with the visualization, because when the number of the particles get high, for example, 200,000 or 500,000, then the visualization becomes a very problematic issue in the post-processing step in every DEM simulation. So by reducing the number of the simulation, the visualization is also a kind of easy task to do. We have, sorry, I just forgot to talk about the two main approaches of the coarse-graining. The first approach is compact grain. It means that I replace the particles, small particles, a number of small particles with a single grain that has the same volume as the original small particles. The other option is the coarse grain. It means that I replace a number of the particles with a particle which is porous, and the number of the particles in the coarse grain is similar to the number of the particles in the original simulation, but I'm replacing a collection of these small particles with a coarse particle. These are the two options or two main approaches in the coarse graining. In the PhasicFlow, we use compact grain for the coarse graining. For compact grain, as I told you, we changed the contact properties and the contact force and other properties that are related to the contact to hopefully get the same behavior in the simulation, both particle scale and bulk scale behavior. We have two main approaches for coarse graining. The first approach is constant absolute overlap. It means that the absolute overlap between the particle in the original simulation should be equal to the overlap between the grain and grain. For example, if the contact properties is such that we have the maximum overlap of 1 millimeter or something like that in the particle-particle contacts, then based on this model, we have the same overlap in the grain-grain contact in the coarse-grained simulation. The other approach is the constant relative overlap. It's almost similar, but here the relative overlap between the particle, I mean that the overlap over the diameter of the particle or diameter of the grain is equal. I'm not going to go into the details of the formulation here. I just refer you to the two articles, Sakai and Radel, to read through these articles and get more insight into these two main approaches. We also have another modification to the model. We call it additional dissipation mechanism or model. This additional dissipation is required because when we have the original simulation, we have more particles in the original simulation than the coarse-grained simulation. If I have more particles, I have more contacts, and during each contact between particles, a part of the kinetic energy is dissipated. When I perform the coarse graining, the number of particles is reduced, so the number of the contacts. So the total dissipation of the kinetic energy is reduced. I somehow should correct this difference. So I just can change the restitution coefficient of the grains with respect to the restitution coefficient of the particles and change the restitution coefficient in the simulation to get the same amount of the kinetic energy dissipation during the simulation when the grains are contacting each other. We have two models for the additional dissipation model. The first model is the one that is introduced by Ben Yahya. We call it GB or simplified in our code. The other is proposed by Lu based on the KTGF theory, and we call it Lu in the code. These are the main concepts of the coarse graining, and as I told you, of course, the details are more than what we can cover in this short course, but if you are interested, you can refer to the articles to get more insight onto the coarse graining.
Okay. Of course, if there are questions about the PhasicFlow and coarse graining, we would be also happy to cover them and answer them. Please get in touch with them through our LinkedIn, through our other channels that we have. So one other point that I wanted to add here, when we are talking about methods like coarse graining, we are talking about bringing models into the simulation. And these are the points that, again, you have to be extra careful. So you have to make sure that the coarse graining is the right approach for what you want to do. Because if you apply a coarse or the coarse graining to a simulation which is not suitable for that, that will lead to wrong results. You might ask me, okay, how should we know about that? My typical old answer is, yeah, go back to your physical knowledge, go back to your physics knowledge, to the particle dynamic knowledge, and check if this behavior can be modeled by collecting a group of particles together or not. Hamid, we also have 2 or 3 questions in the chat, so please also leave one or 2 minutes for that.
Yeah, of course. And I want to add I want to add an example to your explanation. For example, suppose that you are simulating a kind of discharging particles from a hopper, and at the bottom of the hopper we have a small hole. If we increase the diameter of the particles too much, then the grains become very large, and then we have the chance, or we increase the possibility of the blockage of the particles at the exit. And this is something that we should take care, because sometimes coarse graining is not the right answer for a kind of granular flow or multi-phase flow to accelerate the simulation. Okay, here we are going to perform coarse graining on a rotating drum. Every settings is similar to the rotating drum with spherical particles. The only difference here is the case setup, shapes, and interactions. For the shapes, instead of defining the diameter of the particles, I need to define the diameter of the spheres, the original particles, and the diameter of the grains. It means that here, as you see, the diameter of the spheres is 400 micrometer, and the diameter of the grains is 800 micrometer. It means that I am replacing 8 particles with a larger grain with the diameter of 800 micrometer. And in the interaction part, or in the interaction file, I just need to define the proper contact force model and proper dissipation model. As you see here, the contact force model is CG, which refers to coarse graining, relative, which refers to relative overlap, linear refers to the linear model, and limited refers to the type of the friction model that we are using. The normal friction, rolling friction is again normal, and we also have additional dissipation model that I told you. We have 2 options here, Lu and GB. Lu is the one that is proposed by Lu et al., and GB is the one that is proposed by Ben Yahya et al. So, for example, if you want to get the options here to see what options are available in your code, you just need to do the banana method here. The solver for coarse graining is grain-gran-flow. Grain-gran-flow is the solver, and cannot find the intrinsic grain diameters. What I changed here. You just check what just happened here.
So while you're trying to find the error there, maybe I can go through the questions, if it's okay.
Yeah, that's okay.
I would like to know if the simulated case file shown in this live YouTube session is available for download or access. Yes, basically the simulations or the cases that we run are the default tutorial cases which are coming with the PhasicFlow and PhasicFlow Plus, so they're available with the original source code. If you go there, if you go to the tutorial folder, you will find them there. Then the next question, how much did it take time to simulate the simulation for 10 seconds? And what was the system configuration? So that's something that I think, Hamid, you need to answer.
Yeah. I don't remember actually, but it took around 1 hour to perform this 10 seconds of the simulations for the segregation case. The number of particles was 30,000 particles, and I was using a Core i7 8th generation 1.8 gigahertz CPU in the OpenMP mode.
Great. So that was a CPU simulation and not a GPU one.
No, because I don't have any GPU card on my laptop.
Okay, great.
Okay.
Thank you. Then the last question is the book that was introduced at the beginning available in PDF format. I think that should be, or you should be able also to get it as a PDF, but I'm not sure if it's for free.
I think they can find it for free because around 2 months after the publication, it was available for free, of course, from the illegal sites.
Yeah, so if you want to get it legally, so most probably you have to pay for it, but there might be also some other sources that you can get it without paying for it. And okay, 1 hour is good. Yeah, that's one of the things that we are very proud of PhasicFlow and PhasicFlow Plus, because they are performing very well also with medium or low-end hardware.
Yeah, I don't know what is wrong with this simulation, but let me just check something else here. If you have, you just need 2 or 3 extra minutes to.
So we have 3 more minutes. One question, Hamid. Do you have the right version of PhasicFlow active?
Yes. Here I see some. Let me just change it, transfer it to the, because it is somewhere that I'm not sure. Transfer it to the. Desktop, rotating the ROM. Okay. Oh, I just remembered I changed something here. Let me just gram flow. Yes, I changed something before, something in some files before the workshop, and I just forgot to change it back. So again, since I'm streaming, I need to define the number of the threads. OMP num threads equals, for example, 6, 3 cores for simulations, 1 core for streaming. Sorry, I just, yeah. It starts from time 1 almost, because I just transferred somewhere else and continued the simulation somewhere else. That's why you see that it starts from time 1.5. And we were going to see the available results, available options for the contact force. We changed, yeah, we changed this option here to see the available options. And these are the available options: coarse-graining absolute, non-linear limited, and relative non-limited, and so on. If you want to get the list of the available options for the coarse-graining, just do the banana method to list all of the available options for you. The last part is visualizing the results. It's almost similar to the spherical particles, no difference. PhasicFlow to VTK minus binary minus fields, ID, diameter, and maybe velocity are the fields that I'm going to convert. Okay, any questions, Bahram?
No, so far I don't see any questions in the chat.
Okay, I think we ran out of time.
Yes.
It's similar to spherical particles because we are representing grain particles with the spheres. So in the power view, the procedure is the same, particles and surface. Okay, maybe velocity of the particles and see what happens during this simulation. As you see, I am doing coarse grain simulations with coarse graining factor 2. And this is the results up to 1.4 seconds. Of course, we need to perform longer simulation to see the actual results.
Maybe the last question here, Hamid. So what you showed already in the post-processing, were they particles or the grains?
They are grains because we are performing simulations based on the grains. But remember that we are representing, in this simulation, we are representing 8 particles or 8 spheres with a single grain because the coarse graining factor was 2 in this simulation.
Great. Thank you very much.
You're welcome. And yeah, that's it. That's it for this session. I hope you will get what you needed for post-processing and coarse graining. Of course, we didn't cover everything, but again, go through the manual and read the README file on the repository and put your question there if you have any questions. Thank you, everyone, for being with us. Hopefully, we can meet each other in the next week. We are going to talk about CFD-DEM using PhasicFlow Plus. We will start on resolved CFD-DEM, and in the next session after that, we are going to talk about resolved CFD-DEM. Thank you, everyone, and have a good night.
Great. Also, thanks from my side. Thanks for being with us. As Hamid already mentioned, please feel free to get into touch with us to ask questions. And looking forward to see you in the next session with coupling between CFD-DEM, PhasicFlow, and OpenFOAM. Have a great day. Bye.